Hello, dear students. Today I'll talk about set theory, a basic structure of abstract algebra, without which you cannot move into the algebra and calculus. So, set theory is a very important concept in abstract algebra. So, let us find the definition of set theory. It is given by Cantor, a famous German mathematician. A set is a well defined collection of distinct objects viewed as a single entity. So, look at the term well defined collection of distinct objects. So these are the very important concept: collection of distinct objects and the single entity. So well defined. So I will just elaborate the words. A set is a collection of objects which is to be regarded as a single entity. So we'll put a bracket on the entire thing so that it will consider as a single entity. A set S which is distinct objects. So distinct objects means if you have the same elements, then you have to consider only one of them, because there should be a distinct elements. And well defined, it means that if S is a set, we are talking about a set, then A is within the set or is not within the set, definitely not within the set. So if A is an element belongs to the set, we use this is the symbol A belongs to S, this symbol is belongs to. And if A does not belongs to, then we use the symbol this implies does not belongs to S. So this is the symbolic representation of an element belongs to S. Or so for well definedness, A is definitely within S or A does not belongs to S. So this is the definition, and this is the concept of well definedness, distinct object, single entity. Let us have some example for clear understanding. The set of vowels in the alphabet of English language, A, E, I, O, U. So all the, look at that, all the elements are distinct and they are put inside the second bracket, and this is entire thing is a single entity, is called the vowels. So we'll name the set as V. We will use capital letter for the naming of the set. Again we can say, so this is you can count, this is the finite. The set of all odd natural numbers 1, 3, 5, etc., these are the also a set. So we'll again name these odd natural numbers O. So this is also a well defined. The definition is all odd natural numbers and the elements are distinct. So we can express set into two forms: roster method and set builder notations. These above methods are the roster method of putting sets, and set builder means this is the set builders means is a shortcut method or compact method. Suppose if I am talking about a set of real numbers, you know, set of real numbers is a whole real line. It's starting from minus infinity to plus infinity. We can talk about a R. R represents the set of real numbers. So we can write X. The elements of R are X. X is an element of X. R. So what is the property of X? What type of X? X is a real number. So this is the compactness of writing in the set builder form. So in this case also we can write that. Suppose the odd natural numbers, so we can write X. What is X? X is nothing but the odd natural number. X is an odd natural number. X is an odd natural number. So this is the writing. So we can write in this way. So set builder form is more compact form. Suppose set of integers, we know set of integers is 0, plus minus 1, plus minus 2, plus minus 3, etc. So X, we can write X in the set builder form, X such that X is an integer. Also in the rational number, what is rational number? Rational numbers are the numbers of the form P by Q, where P and Q are numbers prime to each other, where P and Q are numbers prime to each other. So this is the form of the rational numbers. This is the form of the rational numbers. So this is the basic examples and few concepts of starting introductions of the set. Next we define subset. Let A and B be two sets. If X belongs to A implies X belongs to B, then we say that A is a subset of B. This means that A is a subset of B written as A. This is the symbol. A is contained in B, or A is a subset of B, or B contains A. There are a lot of languages. We can say A is a subset of B, or A is contained in B, or B contains A. That means B is bigger than A. If and only if every element of A is an element of B. So we say that A is a subset of B if and only if every element of A is an element of B. Every element of A is an element of, but not every there is a element of B which is not in A. It may be. So A is a subset of B, and we say that B is a superset of A. So let us have an example. So I am talking about, this is suppose B and this is your A. So here we see that A is contained in B, or B contains A, or A is a part of B. So that is why we use this term A is a subset of B. So let us have an example. Suppose A is equal to 1, 3, 5, 7 and B is equal to 1, 2, 3, 4, 5, 6, 7, 8 and C is 1, 3. So naturally you see A is contained in B, and C is, you look at the elements of C is contained in A because 1 and 3 are the elements of A, and C is also contained in B. So C is contained in A and C is contained in B. So let us draw C. C is this part. So you see that C is contained in A and C is also contained in B, and A is contained in B. So this is the concept of subset. So we can say that you talk about real numbers. So this is your real number set. Suppose this is your real number set. This is your real number. So real number set of natural number. Suppose real number. So I am talking about a natural number. This is your natural number. Natural number is starting from 1, 2, 3, etc. So this is your natural number. This is your set of integers. Set of integers contain natural number. This is your set of integers. And this is your set of rational numbers. Set of rational numbers contain integers. Set of rational numbers, this is your set of rational numbers, and so on. So our real number contains rational number, set of integers, and set of natural number. So Z contains n, and we say Q contains n, and also you are talking about real numbers, but there is a number which contains real number, which are complex numbers. These are the much bigger field. So this is your complex number, set of complex numbers. So all the real numbers are complex numbers. We'll see in the lectures of complex number later on. So next move on to what is null set. A set containing no elements. If there is no element, then that set is a null set. It's a concept, or the empty set, or the void set, and is denoted by the symbol phi. Null set. Suppose I am talking about an example. Suppose X. I am talking about a set S. Elements of S is X, such that X is a real root of X is a real root of X square. Sorry, X is a real root of X square. This is square plus 1 equal to 0. So is there in a real root of x square plus 1 is equal to 0? No, there is a complex roots. So there is no real root. So this gives you a null set. So elements of S are null set. So in such a way we explain the null set. So now For every set S is a subset of itself. This is the concept of subset, from the concept of subsets, and phi is a subset of every set. This is also from the definition of subset. So these are called improper subsets of S. These are called improper subsets of S. So for every set is a subset of itself, and phi is a subset of itself. Phi is a subset of that set, every set. So this is the improper subsets. Any other subset of set to be a proper subset of S. Universal set. Universal set is a set. We are talking about a constant set. In any set discussion of a single set which is involved fixed set, that set is said to be a universal set. Suppose we are talking about a planetary system. So our universe, we are talking about planets and all the stars are the part of this. So universe, that is the concept of this universal set. Universal set, we are taking a fixed set as a father or mother set, and all the elements are its subsets. So that is the concept of universal set. Next, we are talking about a finite set or infinite set. A set, already we have so many examples of finite set and infinite set. A set is said to be finite if it is empty or contains a finite number of elements. Otherwise, it is said to be an infinite set. Suppose the set of real numbers, set of integers, set of rational numbers, set of natural numbers, all are infinite set. And we are talking about a set of vowels, that is a finite set. Clear? Next, there is a concept of equality of two sets in A and B. Like in real number, two numbers are equal. Equal means x equal to 5, we say, but in sets that is not true. So we have to think very carefully about the equality of two sets. How will you say that two sets are equal? If A is a subset of B and B is a subset of A. That means all the elements of A are in B and all the elements of B are in A. Then in that case only we can say that two sets are equal. If the number of elements are same, we cannot say that these two sets are equal. Suppose A, E, I, O, U, 5 elements in a set, and suppose take an example of a set 1, 2, 3, 4, 5. So these two sets have that same number of elements, 5, 5, but they are not equal. Look at that example, a set containing 2, 3 and a set containing x such that x square minus 5x plus 6 is equal to 0. That means the values of x. So in this case, if you solve, you will get 2 and 3. So these two sets are equal sets. Clear? Very important concept next, power set. What is a power set? Power set of a set A, suppose unique set whose elements are all subsets of A. That means power set is a set which contains all the subsets of A. So let us have an example. Suppose 1, 2, 3. A is an A, 1, 2, 3. Then the power set of A is given by phi, because already we know that phi and A are the improper subsets. So phi is a subset of A and the set itself is a subset of A. If you take single elements, these are the subsets 1, 2, 3. They again two elements at a time, 1, 2, 1, 3, 2, 3. So these are the proper subsets of proper and improper subsets of A. So these are all collection of all subsets of A, and this is called the power set of A. Look at that, there are 8 elements and a set contains 3 elements, its power set contains 8 elements. So we can say that if a set finite set contains n elements, then its power set contains 2 to the power n elements. Okay. Next we talk about operations of sets. Union. First operation, union or join of two sets A and B is a subset of U, and U is the universal set denoted by A union B. This is the notation for union. Union, what is the union? Union in X such that X belongs to A or X belongs to B. Either X belongs to A or X belongs to B. So let us have example for that. So 2, 4, 6 and union of 2, 6, 10, 14. So union will be 2, 4, 6 already in A. So 2, 4, 6 take, and extra elements in B are 10, 14. So you take all the elements. Don't take twice because only a single element should be there. So this is the union. Let's have a Venn diagram. Scientists Venn have introduced a beautiful concept to describe sets. So this is the Venn diagram. This is A set and this is B set. This is A set and this is B set. So this is universal set. This is actually universal set. This is actually universal set. This square is the universal set. So this is A and B. So what is the union of A? You take all the elements of A, and you take all the elements of B. So there are some common elements also, that is also included. So your A union B is nothing but those elements either in A or in B or in B both. So this is the concept of union. Look at the examples also and look at the Venn diagram also. Next, intersection. What is the intersection? Intersection is given by A intersection B such that X belongs to A, and in the case of union there is or, and in the case of intersection there is and. So A intersection B is the set of all those elements which belongs to the both A and B. It follows that A intersection B is a subset of A and A intersection B is a subset of B. So you look at the example again. 2 4 6 intersection 2 6 10 14. What will be the intersection? 2 6, because 2 6 is the common element only. So let us have a diagram of Venn diagram also for the in this case also. Let us have a Venn diagram. This is the universal set. This is the universal set, A set and B set. So this is the common area. So this is A intersection B. So intersection B means A and B. That is the common region only. Union, the whole region that is in A or B both. Disjoint means A intersection B is equal to phi. That is, there is no common region. So let us have a diagram of disjoint sets. So this is again a Venn diagram. A set, B set. So look at that, there is no common intersection. So in this case we say A intersection B is phi. A and B are disjoint or mutually exclusive sets. We say also mutually exclusive sets. Next, complementation. Complementation means the complement of a subset of A is denoted by A dashed or AC and is denoted by A prime. We can say prime also. A prime is equal to X belongs to U, universal set, but X does not belongs to A. So let us have a Venn diagram for a clear understanding. So this is your A, this is your A set, so this is your A set. So your complementary part is the external region. This is your complementary part, that is the universal set. So we say X belongs to the universal set but X does not belongs to A. So this external part outside the circle is the complementary part. So if your universal set is 1 2 3 4 5 6 and A is 1 3 5, what is your complementary part? 2 4 6, which are not in A. Difference of two sets. Next we define A union A minus B. A minus B is difference of two sets. X belongs to A and X does not belongs to B. So we say with a diagram, again with a Venn diagram, this is your A, this is your B, this is your A, this is your B. So this part is your A minus B, this part is your A minus B, and this part is your B minus A. So A minus B, that is contained in A but not in B, and this is B minus A. B, X belongs to B but not in A. So this is your A minus B and this is your B minus A. Look at that, they are disjoint, mutually exclusive. Also we can say A minus B as A intersection B complement. A intersection B complement, because X belongs to A and X does not belongs to B implies X belongs to B complement. So that is why A intersection B complement. So let us have an example for that. A is equal to 2 4 6 and B is equal to 2 6 10 14. So A minus B is 4 and B minus A is 10 comma 14. Look at from this example and also from the Venn diagram. Also we define symmetric difference, that is A delta B as A minus B union B minus A. This is also a concept of symmetric difference. Properties, there are some important properties for sets. A union phi is equal to A intersection phi is equal to phi, A union universal set is equal to universal set, A intersection union is equal to A union A is equal to A intersection A is equal to A. This is called idempotent property. And A union, this is very important, A union A intersection B is equal to A. This is called absorptive property. A intersection A union B is equal to A. This is important property. And also we have commutative property, A union B is equal to B union A. Just like addition is a commutative property, A plus B is equal to B plus A in real numbers, and A intersection B is equal to B intersection A. Also we have associative property, A union B union C is equal to A union B union C. And also for this the same thing is for the intersection also. Distributive property, A union B intersection C is equal to A union B intersection A union C, and A intersection B union C is equal to A intersection B union A intersection C. So let us have a proof of that. Let P is equal to this set A union B intersection, and Q is equal to A union B intersection A union C. Let X be an element of P. So X belongs to P implies X belongs to A, there is a union, so we can write or X belongs to B intersection C. Also for intersection, which implies intersection, we can say X belongs to, for intersection we use the word and, so we can say X belongs to B and X belongs to C. So we can write which implies X belongs to A or X belongs to B and X belongs to A or X belongs to C. So X belongs to or means A union B and X belongs to A union C. So we have X belongs to A union B intersection A union C. So we have assumption that X belongs to P and we prove that X belongs to Q. So what is from the definition of subset, we can say P is a subset of Q. Again similarly we can prove letting Y be an element of Q, that Y belongs to P. Same way, in the same way we can prove, so Q is a subset of P. So we prove that P is a subset of Q and Q is a subset of P. So from the definition of equality of sets we can say P is equal to Q. So that in that way we prove the distributive property. Similarly we can prove the second distributive property. Next we'll see De Morgan's law. De Morgan's law is very important. A union B complement, whole complement is A complement intersection B complement, and A intersection B complement is equal to A complement union B complement. This is very important, De Morgan's law. So I will prove that first part. Let P is equal to, again similarly for proving, P is equal to A union B whole complement, Q is equal to A complement intersection B complement. So X be an element of P. X belongs to P implies X belongs to A union B whole complement. So if it is in the complementary part, then it is does not belongs to the A in union B, because complementary part we know from the definition of complement, if an element is an element of a complementary part, it is does not belong to the set, so it does not belongs to A union B. So X does not belongs to union means X does not belongs to A and X does not belongs to B, because if it would have been in A and B, then it must be in A union B. So it does not belongs to A union means it does not belongs to A and does not be, if it is does not belongs to A, then implies X belongs to A complement from the definition of complement, and X belongs to B complement. So X belongs to A intersection B, A complement intersection B complement. So X belongs to Q. So P is a subset of Q. Again similarly we can say Y be an element of Q, and same process we can show that Q is a subset of P. So combining 1 and 2 we see that P is a subset of P is equal to Q. This is the first proof of the De Morgan's law. Similarly with the help of this you can prove the second one also. Also we say for a finite set, this is the last part of our topic, the number of elements in a set is denoted by NA, number of elements, and n of A union B is n of A plus n of B minus n of A intersection B, and if n of A intersection B is 5, then n of A plus n of B, this part is 0. So let us have a diagram for clear understanding. This is your A, this is your B, So this is the number of elements in A and this is the number of elements in B. Look at that, this region comes twice, so there is a subtraction of n of A intersection B. That is why, that is n of A union B is equal to n of A plus n of B minus n of A intersection B. But if they are disjoint, that is mutually exclusive, no intersection, then n of A plus n of B. Also we can say n of A minus B, n of A is equal to n of A minus B plus n of A intersection B. That is from this picture. This is your n of A minus B, this is your n of A minus B, and n of A is nothing but your n of A minus B plus n of A intersection B. Similarly, n of B we can define. This property actually this formula actually we use in the problems, lot of problems in set theory. Suppose our students takes English as a language, physics as a, and Bengali as a language, and Hindi as a language. So in those problems, those students taking English and Hindi, English and Bengali, so this type of problems, dealing with this type of problems, we can use this type of formula. So today's lecture where I am finishing there here. So dear students, I think this video will be helpful for you for clear understanding of the set theory and the basic concept of set theory. Thank you all.